Hi everyone, now we are going to discuss about algorithm analysis framework. In this presentation, we will learn how to evaluate the performance of algorithms. Designing an algorithm is the only the first step. We must also determine whether it is efficient in terms of execution time and memory usage. This analysis helps us compare different algorithms and choose the most suitable one for solving a problem. Algorithm analysis is the process of measuring an algorithm's efficiency. There are two important measures. The first is time efficiency, which tells us how quickly an algorithm executes. The second is space efficiency, which tells us how much additional memory the algorithm requires during execution. A good algorithm should minimize the both execution time and memory usage. Aspects of the analysis framework. So the algorithm analysis framework consists of four important aspects. First one, measuring the input size. Second, measuring the running time. Third, studying the order of growth of algorithm. And finally, analyzing the algorithm under worst case, best case and average case conditions. So though those affect aspects helps us understand how an algorithm behaves for different input sizes. Measuring input size. Algorithm efficiency is always expressed as a function of the input size. The definition of the input size depends on the problem. For sorting algorithms, the input size is number of elements represented by n. For matrix addition, the input size depends on the number of elements in the matrix, which is n square. For numerical problems, the input size may be measured using the number of bits required to represent a number. Choosing the correct input size is the first step in performance analysis. Units for measuring running time. So measuring execution time using seconds or milliseconds is not reliable because it depends on the processor speed and hardware configuration. Instead, algorithm analysis counts how many times important operations are executed. Although counting every operation is difficult, we normally count only the algorithm's basic operation, which contributes the most to the total running time. A basic operation is the most frequently executed or the most time consuming operation in an algorithm. Usually it appears inside the innermost loop. For example, in searching algorithm, the basic operation is key comparison. In matrix addition, it is addition. In polynomial evaluation, it is multiplication. Counting the number of basic operations gives us a good estimate of the running time. The order of growth describes how the running time increases as the input size increases. Instead of considering every term in a mathematical formula, we focus only on the leading term because it dominates the running time for larger inputs. So in this table compares different growth functions as the input size increases, logarithmic and linear algorithms remain efficient. Quadratic and cubic algorithms become slower. Exponential and factorial algorithms grow extremely fast, making them impractical for large inputs. Therefore, algorithms with lower growth rates are generally preferred. So among common growth functions, logarithmic complexity represented as big O of log n grows the slowest and is highly efficient. Algorithms like binary search belong to this category. On the other hand, exponential big O of 2 power n and factorial big O of n factorial complexities grow extremely fast. These algorithms become impractical even for moderate input sizes because their execution time increases dramatically. So this table shows what happens when the input size doubles. For a linear algorithm, execution time doubles. For an big O of n log n algorithm, it increases slightly more than double. Quadratic algorithm become 4 times slower. Cubic algorithm become 8 times slower. And exponential algorithm become dramatically slower. So this comparison clearly shows why efficient algorithms are important. So some algorithm perform differently depending on the input. Consider the sequential search algorithm shown here, and if the required element is at the beginning of the list, the search is very fast. If it is at the end or absent, the algorithm takes much longer. Therefore, we analyze algorithm under these three cases, that is, the worst case is the situation where the algorithm takes the maximum possible time. For sequential search, the worst case occurs when the element is not present or is located at the last position. The algorithm compares every element. Therefore, worst case of n equal to n comparisons. So, worst case analysis provides an upper bound on the running time. The best case is when the algorithm performs the minimum amount of work. In sequential search, this happens when the desired element is found in the very first position. Only one comparison is required, so the best of n equal to 1. Although the best case performance is useful to know, algorithms are usually compared using worst case analysis. The average case efficiency, it represents the expected performance for a typical input. It is important to note that average case is not simply the average of the best and worst cases. Many algorithms perform much better on average than in the worst case. So this makes average case analysis valuable in practical applications. For sequential search, suppose the probability of finding the element is represented by P. The search is successful, the average number of comparison depends on whether where the element is located. If the search is unsuccessful, all the elements are compared. So these probabilities are combined to calculate the expected number of comparisons. The average case complexity of the sequential search is given by this formula when the search is always successful, meaning p equals 1, the average number of comparisons become n plus 1 divided by 2. When the search is always unsuccessful, meaning p equals 0, the algorithm compares all n elements. So this formula helps estimate the expected running time. So average case analysis is often difficult. We first classify all the possible inputs based on how many basic operations they require. Then we assign probabilities to each class. Finally, we calculate the expected value of running time. So because the estimating input probabilities is challenging, the average case analysis is usually more complex than worst case analysis. So amortized efficiency. Sometimes a single operation may be very expensive, while most other operations are inexpensive. Instead of analyzing each operation individually, we spread the cost of expensive operation across many operations. This technique is called amortized analysis. A common example is resizing a dynamic array. Although resizing takes longer, it happens infrequently, so the average cost per operation remains small.